Right now, at this very moment, there's a hole in the sun the size of 60 Earths, and it's pointing straight at us like a cosmic gun barrel. The sun doesn't just have bad days, it has catastrophic ones. And according to data streaming in from solar observatories, we might be staring down the barrel of one right now. They're calling it Goliath. An interstellar visitor just passed by. California's magnetic readings are going haywire. The planets are aligning. And some people are saying, this isn't coincidence, it's a countdown. Stay with me until the end, because what's actually happening is far stranger than the headlines suggest. And the truth sits somewhere between utter catastrophe and perfect cosmic timing that nobody saw coming. You'll want to follow along as Threeey Atlas slips deeper into the solar system. Subscribe now, because this story is far from over. The answers we've been chasing are closer than ever, and you'll want to be here when everything finally clicks into place. Something happened to the sun 3 weeks ago that wasn't supposed to happen. Not like this. Not now. You're scrolling through your feed on a Tuesday morning, coffee in hand, expecting the usual noise. Instead, you see a headline that stops you cold. The sun has torn open. A massive wound stretching across its surface, a chasm in its magnetic skin, and it's pointed directly at us. They're calling it a trans-equatorial coronal hole. The word Goliath keeps appearing, and beneath that, another line that makes your stomach drop. Earth's magnetic shield is failing. This isn't science fiction. This is happening right now as you read these words, as the solar wind screams toward our planet at speeds that would make a bullet train look like it's standing still. Let me explain what a coronal hole actually is, because the reality is both less terrifying and more fascinating than the headlines suggest. Imagine the sun as a sphere wrapped in invisible magnetic field lines, like rubber bands stretched around a beach ball. Most of the time, these field lines loop back into the sun, keeping the solar atmosphere contained. But sometimes, in certain regions, those field lines don't loop. They open. They reach out into space, like fingers stretching into the void. And when that happens, the solar wind, that constant stream of charged particles the sun is always emitting, finds an express lane. It rushes out at speeds of 600 to 800 kilometers per second, sometimes faster. These are coronal holes. They appear dark in ultraviolet images because they're cooler and less dense than their surroundings. They're not rare. They happen all the time, especially during certain phases of the solar cycle. But this one is different. On December 6th, 2025, active region 4299, a cluster of sunspots on the sun's surface, unleashed an M8.1 solar flare. That's a powerful flare, strong enough to cause radio blackouts on Earth. But the flare wasn't traveling alone. It launched a coronal mass ejection, a CME, a billion-ton cloud of magnetized plasma hurling directly toward Earth. NOAA's Space Weather Prediction Center issued a G3 geomagnetic storm watch for December 9th. G3 is classified as strong, not catastrophic, not apocalyptic, but strong enough to disrupt GPS systems, affect power grids, and paint the sky with auroras visible far south of their usual territories. Scientists measure these disturbances using something called the K-index, a scale that tracks variations in Earth's magnetic field. During quiet times, the K-index hovers around 0 or 1. During a G3 storm, it spikes to 7 or 8. At G5, the highest level, we're talking about the kind of event that could cripple satellites and knock out power across entire continents. We're not there. Not yet. But here's where it gets strange, where the data starts whispering things that make even the skeptics pause. Trans-equatorial coronal holes, holes that stretch from one hemisphere of the sun to the other, are unusual late in solar cycle 25. We're supposed to be approaching solar maximum, the peak of the sun's 11-year activity cycle, when sunspots multiply and flares become common. Coronal holes typically dominate during the declining phase when the sun starts to calm down. Their appearance now suggests the sun isn't following the script. It's improvising. And it's improvising at the exact moment something else is happening in our solar system. Something that, according to some, shouldn't be a coincidence. On July 1st, 2025, NASA's Atlas survey detected an object moving through space with a trajectory that defied everything we know about objects native to our solar system. Its orbit was hyperbolic. It wasn't bound to the sun. It came from somewhere else. They named it Threeey Atlas, the third confirmed interstellar object ever discovered. The first was Oumuamua in 2017. The second was Comet Borisov in 2019. Both passed through and vanished, leaving more questions than answers. Threeey Atlas is different. It's not just passing by, it's approaching. On December 19th, 2025, just days from now, it will make its closest approach to Earth. Not close enough to worry about, not by astronomical standards. 1.8 astronomical units, roughly 270 million kilometers. That's farther than the distance between Earth and the Sun. Safe, harmless, nothing to see here. Except some people are seeing something. They're connecting dots that on paper shouldn't connect. They're asking why a trans-equatorial coronal hole opened just as an interstellar visitor swings through our neighborhood. They're asking why geomagnetic readings from California, specifically over the San Andreas Fault, are showing patterns that don't fit the models. They're using words like resonance structures and spectral anomalies. They're claiming the shield is down. Let's be clear about what Earth's magnetic shield actually is. It's not a force field. From Star Trek, it's not a bubble we can switch on and off. It's a consequence of our planet's molten iron core spinning and generating electric currents, which in turn generate magnetic field lines that extend tens of thousands of kilometers into space. These field lines deflect most of the charged particles the sun throws at us, funneling them toward the poles, where they collide with our atmosphere and create auroras. Without this field, solar wind would strip away our atmosphere over millions of years, the way it stripped away Mars's atmosphere when its magnetic field collapsed. But our field isn't failing. Not globally, not suddenly. There is, however, a region where it's measurably weaker. It's called the South Atlantic Anomaly, a zone stretching from South America to Southern Africa, where the magnetic field dips closer to Earth's surface. Satellites passing through the anomaly experience higher radiation exposure. Astronauts on the International Space Station take extra precautions when orbiting through it. It's been tracked for decades. It's real, it's documented, and it's slowly moving westward. But it's not a crack. It's not a failure. It's a feature of a dynamic system. The claims about California are different. They're specific. They're local. And they're not showing up in peer-reviewed journals. They're showing up on forums and in videos narrated by voices that mix genuine curiosity with apocalyptic certainty. They point to magnetometer readings, graphs with jagged lines, and color-coded intensity maps. And they say, look, right there, over the fault. The field is collapsing. Mainstream scientists aren't saying that. They're saying solar wind is hitting Earth's magnetosphere the way it always does during active periods. They're saying auroras will be beautiful. They're saying radio operators might experience disruptions. They're saying expect some satellite hiccups and maybe voltage irregularities in power grids at high latitudes. They're not saying the shield is down. But what if the fringe voices are seeing something the models aren't built to detect? What if the timing really does matter? What if an interstellar object, even one as distant as Threeey Atlas, carries with it forces we don't yet understand? Because here's the thing, nobody's talking about publicly, but everyone's thinking privately. We've only observed 3 interstellar objects, ever. We have no baseline. We have no comparative data. We're working with a sample size so small it's laughable by scientific standards. And now, one of them is approaching during a period of unusual solar activity, and people are claiming to see patterns in Earth's magnetic field that shouldn't be there. Coincidence? Probably. Almost certainly. But the word almost is doing a lot of work in that sentence, and the sun isn't finished with us yet. Let's talk about what a magnetic field failure would actually look like, because the phrase gets thrown around like it's a switch that flips from on to off, and that's not how planetary magnetism works. Earth's magnetic field is generated deep in the outer core, where liquid iron churns in convective currents driven by heat escaping from the inner core. This motion, combined with Earth's rotation, creates what's called a dynamo effect. Electric currents flow through the conductive iron, and those currents generate magnetic field lines that emerge from near the South Pole, arc through space, and re-enter near the North Pole. It's a self-sustaining system that's been running for billions of years. When people say the shield is failing, they're imagining a scenario where this system breaks down. And it can. It has. The geological record shows that Earth's magnetic field has reversed hundreds of times over the past 100 million years. North becomes south, south becomes north. During the transition, which can take thousands of years, the field weakens significantly. It doesn't vanish entirely, but it becomes chaotic, with multiple poles appearing and disappearing like glitches in a failing hard drive. The last reversal happened 780,000 years ago. We're overdue, statistically speaking, but overdue in geological terms means nothing on human timescales. It could happen tomorrow. It could happen in 50,000 years. But a localized failure? A sudden collapse over a specific fault line? That's not how the dynamo works. The field is global. Weaknesses are broad, slow-moving, and measured over decades or centuries, not days or hours. So where is this idea coming from? It starts with real data taken out of context. Magnetometers placed along the San Andreas Fault do record fluctuations. They're supposed to. Seismic activity generates electromagnetic signals. Tectonic stress changes the conductivity of rock. Water moving through fractured crust alters local magnetic properties. These are known effects, studied and understood. They're not evidence of a collapsing planetary field. They're evidence of a geologically active region doing what active regions do. But then someone overlays those readings with data from the coronal hole. They notice the timing. High-speed solar wind hits Earth's magnetosphere on December 9th. Magnetometers along the San Andreas show unusual activity around the same time. And they say, there, connection. Is there? Probably not in the way they think. Solar wind does interact with Earth's magnetic field, compressing it on the day side and stretching it into a long tail on the night side. These interactions generate currents in the ionosphere and the upper atmosphere, which can induce currents in the ground. These ground-induced currents can, in theory, affect magnetometer readings, but they don't weaken the planetary field. They're a symptom of the field doing its job, deflecting and absorbing energy from the solar wind. Now let's bring Threeey Atlas back into the picture, because this is where the narrative gets truly speculative and, admittedly, kind of fascinating. Interstellar objects are pristine samples of material from other star systems. They formed in protoplanetary disks around stars we'll never visit, ejected by gravitational interactions, and spent millions or billions of years drifting through the galaxy before stumbling into our corner of space. Threeey Atlas originated somewhere in the Milky Way, probably within a few hundred light years of us, and its trajectory brought it into the inner solar system along a path that will carry it back out into interstellar space. It's not going to hit us. It's not even going to come particularly close. At its nearest approach on December 19th, it will be farther from Earth than Mars is right now. The gravitational influence of such a small object at such a distance is negligible. We're talking about forces so weak they wouldn't nudge a grain of sand. But some communities online are connecting it to the solar activity anyway, not through gravity, through something else, something harder to pin down: electromagnetic fields, plasma interactions. The idea that an object carrying interstellar material might disturb the local space environment in ways we don't yet understand. Is there any evidence for this? No. None. Not a shred. Is there any reason to think it's plausible? Also no. The solar wind doesn't care about comets. It flows past them the same way wind flows past a pebble in a stream. Comets have their own interactions with the solar wind, forming plasma tails and bow shocks. But those are local phenomena contained to the comet's immediate vicinity. They don't propagate across astronomical units to affect planets. And yet, the narrative persists. Why? Because the timing feels too perfect. Threeey Atlas makes its closest approach on December 19th. The trans-equatorial coronal hole opened in early December. The CME hit on December 9th. A historic planetary alignment is scheduled for January 6th. If you're looking for a pattern, you'll find one. The human brain is wired to detect patterns. It's how we survived as a species. The rustle in the grass might be wind, or it might be a predator. Better to assume predator and be wrong than to assume wind and be dead. We're applying that same instinct to cosmic events. We see the comet, the coronal hole, the geomagnetic storm, and the alignment, and our brains scream, this means something. Maybe it does. Just not what we think. Let's zoom out for a second and look at the actual science timeline. Solar activity is driven by the sun's magnetic field, which follows an 11-year cycle of waxing and waning intensity. Sunspots, flares, and CMEs are products of magnetic reconnection events in the sun's atmosphere. These events are influenced by internal dynamics within the sun, by the rising and twisting of magnetic flux tubes through the convective zone. They're not influenced by planets. They're not influenced by comets. The sun is too massive, too energetically dominant. External objects don't move the needle. Coronal holes form when magnetic field lines open into space, usually near the sun's poles during solar minimum, but increasingly at lower latitudes as the cycle progresses toward maximum. The appearance of a trans-equatorial hole late in the cycle is unusual, but not unprecedented. It's a sign that the sun's magnetic configuration is more complex than the simplified models predict. That's interesting. That's worth studying, but it's not evidence of external influence. It's evidence that the sun is complicated. Threeey Atlas is a passenger here, not a driver. It's witnessing the solar system's weather, not creating it. And yet, if you're reading this and feeling a pull toward the idea that maybe, just maybe, there's something we're missing, you're not alone. Because the truth is, we don't know everything. We're still learning. And sometimes the fringe is where the next breakthrough hides. But not today. Not with this. Let's talk about planetary alignments, because if you've spent any time online in the past month, you've probably seen the January 6th date circulating like a prophecy. On January 6th, 2025, Earth, Jupiter, Venus, Mars, Saturn, and Uranus will appear to align in the sky as viewed from Earth. I say appear because they won't actually be in a straight line. Alignment, in astronomical terms, is loose. It means the planets are positioned in roughly the same region of the sky, within a few degrees of arc. They're not stacked like billiard balls. They're scattered across their orbits, millions of kilometers apart, just happening to share a similar angle from our perspective. This happens regularly. Planetary alignments are a consequence of orbital mechanics. The planets move in predictable elliptical paths around the sun, and occasionally their positions coincide in ways that create visually interesting configurations. It's beautiful, it's photogenic, and it's utterly harmless. But the narrative around January 6th is different. It's not about aesthetics, it's about causation. The claim is that this alignment combined with the ongoing solar activity and the presence of Threeey Atlas, will trigger a geomagnetic event on par with the Carrington event of 1859. For those unfamiliar, the Carrington event is the gold standard of solar storms. In early September 1859, amateur astronomer Richard Carrington observed a massive solar flare through his telescope, a bright flash on the sun's surface, visible even through the protective filters he was using. Hours later, a coronal mass ejection slammed into Earth's magnetosphere with unprecedented force. Auroras appeared as far south as the Caribbean. Telegraph systems across Europe and North America sparked and caught fire. Operators reported receiving electric shocks. Some telegraph lines continued transmitting messages even after their power sources were disconnected, drawing energy directly from the geomagnetic currents induced by the storm. If a Carrington-level event hit today, the damage would be catastrophic. Our modern infrastructure is far more vulnerable. Power grids would fail. Satellites would be fried. GPS would go dark. Communication networks would collapse. We're talking about trillions of dollars in damage and years of recovery time. So the question becomes, could the January 6th alignment trigger such an event? The short answer is no. The long answer is still no, but with more nuance. Planetary alignments do not cause solar flares. They don't cause coronal mass ejections. They don't influence the sun's magnetic field in any measurable way. The gravitational forces exerted by the planets on the sun are real, but they're infinitesimally small compared to the forces generated by the sun's own mass and rotation. Jupiter, the most massive planet, exerts a gravitational pull on the sun equivalent to a flea tugging on an elephant. The other planets contribute even less. There is no physical mechanism by which planetary positions could trigger solar activity. The sun's behavior is governed by its internal magnetic dynamics, by the turbulent convection of plasma in its outer layers, by the shearing and twisting of magnetic field lines over days and weeks and months. Planets are bystanders, but the idea persists. And it persists because of two things: historical coincidences and pattern recognition. Throughout history, people have recorded unusual celestial events coinciding with alignments. Sometimes those events were real, like earthquakes or eclipses. Sometimes they were imagined, projected onto the sky by cultures looking for omens. The human record is messy, full of confirmation bias and selective memory. We remember the hits and forget the misses. In 1859, there was no notable planetary alignment. The Carrington event was caused by a solar flare and CME period. The planets had nothing to do with it, but if you squint hard enough, you can find planets in certain configurations during any major historical event. It's a numbers game. With 8 planets orbiting at different speeds, there's always something happening in the sky. The January 6th alignment is being framed as a once-in-a-lifetime configuration, but it's not. Similar alignments have occurred before and will occur again. The rarity is exaggerated. What's genuinely rare is the convergence of narratives. The coronal hole, the CME, the geomagnetic stormwatch, Threeey Atlas, and now the alignment. Each element on its own is mundane. Together, they form a story that feels significant, even if the significance is purely psychological. And here's where it gets tricky, because even skeptics have to admit that the sun is capable of surprise. We don't have perfect predictive models. Solar physics is hard. The sun is a seething ball of plasma with magnetic fields so complex they make Earth's weather look simple by comparison. Flares can erupt with little warning. CMEs can launch in unexpected directions. The timing of solar maximum is uncertain. Could we get hit by a Carrington-level event in the next few weeks? Technically, yes. It's always possible. Solar cycle 25 has been more active than initially predicted, and we're still climbing toward the peak. The sun is primed. But it won't be because of the planets. It won't be because of Threeey Atlas. It will be because the sun's magnetic field is in a state of instability, and magnetic reconnection events are inherently chaotic. If a Carrington-level CME launches toward Earth, it will be bad luck, not cosmic alignment. And yet, the framing matters. The way we tell the story shapes how we feel about the risk. If we frame it as random chance, it's abstract and distant. If we frame it as the planets are aligning, it feels intentional, meaningful, like the universe is sending a message. The universe isn't sending a message. The universe doesn't care. But we care. We need stories. We need meaning. And sometimes the most compelling stories are the ones that blend just enough truth with just enough speculation to make you wonder. So here we are, wondering. The sun has opened a wound in its atmosphere. An interstellar visitor is passing by. The planets are lining up, and in the back of our minds, a voice whispers, "What if? What if we're missing something? What if the models are wrong? What if the next few weeks bring something none of us saw coming?" We'll find out soon enough. But first, let's talk about what's actually driving the solar storm engine. Because understanding the mechanics makes the speculation either more or less terrifying, depending on your perspective. The sun is not calm. It's never been calm. It's a continuous explosion held together by its own gravity. A ball of hydrogen fusing into helium at a rate of 600 million tons per second, releasing energy that travels 93 million miles to warm your face on a summer afternoon. But that warmth is the least interesting thing the sun does. What's far more interesting and far more dangerous is what happens when the sun's magnetic field gets tangled. Because the sun isn't solid. It doesn't rotate uniformly. The equator spins faster than the poles, completing a rotation every 25 days, while the poles lag behind at 35 days. This differential rotation twists the magnetic field lines that thread through the sun's plasma like strands of wire woven into a spinning sphere. Over time, those field lines wrap around each other, kinking and buckling until they can't take the stress anymore. And then they snap. This is magnetic reconnection, the process that drives solar flares and coronal mass ejections. When field lines reconnect, they release energy that's been building up for days or weeks. Energy equivalent to billions of nuclear bombs detonating simultaneously. That energy accelerates charged particles to near light speed and heats plasma to tens of millions of degrees. The plasma erupts from the sun's surface in a fountain of fire, a coronal mass ejection, carrying with it a billion tons of solar material traveling at speeds of up to 3,000 kilometers per second. If that eruption is aimed at Earth, we have between 15 and 18 hours to prepare. That's how long it takes for the CME to cross the space between the sun and our planet. Satellites detect the flare immediately. The burst of X-rays and extreme ultraviolet light that arrives at the speed of light 8 minutes after the event. Then comes the wait. The slow, inevitable approach of the plasma cloud. On December 6th, active region 4299 did exactly this. Sunspot clusters near the sun's equator had been growing for days, their magnetic fields intensifying, twisting, preparing to release. At 12:43 UTC, the region flared. An M8.1 flare, classified as moderate to strong, the kind that causes radio blackouts on the day side of Earth by flooding the ionosphere with X-rays. Radio operators in the Americas and the Pacific lost contact for minutes as the sudden ionization absorbed their signals. But the flare was just the opening act. The main event was the coronal mass ejection that followed. Coronagraphs on board the Solar and Heliospheric Observatory captured the eruption as a bright halo expanding around the sun, a full halo CME, meaning the plasma cloud was heading directly toward or away from Earth. In this case, toward. NOAA's Space Weather Prediction Center ran the models. They calculated the CME's speed, its density, its magnetic orientation. They issued a G3 geomagnetic storm watch for December 9th, warning that when the CME arrived, it would compress Earth's magnetosphere and inject energy into the Van Allen belts, the radiation-filled regions surrounding our planet. Auroras would flare. Power grids at high latitudes would experience voltage fluctuations. Satellites would need to adjust their orbits to compensate for increased atmospheric drag as the upper atmosphere heated and expanded. And that's exactly what happened. The CME hit on schedule. The magnetosphere shuddered. Auroras painted the sky green and red as far south as northern Europe and Canada. It was spectacular. It was predictable. It was routine. Except for one thing: the coronal hole. Coronal holes and CMEs are different beasts. A CME is a discrete event, a single blast of plasma. A coronal hole is a persistent feature, a region where the sun's magnetic field is open to space, allowing a continuous stream of high-speed solar wind to escape. Normally, the solar wind that reaches Earth travels at around 400 kilometers per second. Wind from a coronal hole can hit 800 kilometers per second or more, and when a coronal hole faces Earth, the effects can last for days. The transequatorial coronal hole that opened in early December is massive. Satellite observations show it stretching from the northern hemisphere to the southern hemisphere, spanning more than 30 degrees of solar latitude. It's not unprecedented. Large coronal holes have appeared before, but the timing is strange. Late in solar cycle 25, as we approach solar maximum, coronal holes should be smaller and less frequent. Their presence suggests the sun's magnetic field is in a more chaotic state than expected. Some are calling it the Goliath hole. The name is dramatic, evocative, and mostly unsupported by official sources. NASA and NOAA haven't issued any statements calling it Goliath. The term appears to have originated in online space weather communities and spread through social media. It's a branding exercise, a way to make the coronal hole sound more threatening than it actually is. But here's the thing: even without the branding, large coronal holes are worth paying attention to. They're not catastrophic, but they're disruptive. The high-speed wind they emit can interact with Earth's magnetosphere for extended periods, causing sustained geomagnetic activity. If a CME arrives while the coronal hole's wind is already battering our magnetic field, the combined effect can amplify the storm. This is what happened around December 9th. The CME hit while the coronal hole was still facing Earth. The two streams of plasma, one explosive and dense, the other fast and sustained, collided in the space around our planet. The magnetosphere absorbed the impact, deflecting most of it, but the energy had to go somewhere. It went into the ionosphere, into auroras, into induced currents in the ground. And that's where the claims about California start to sound less ridiculous. Not because the shield is failing, but because ground-induced currents are real. They're measurable. They're a known consequence of geomagnetic storms. If magnetometers along the San Andreas Fault detected unusual activity around December 9th, it's because the geomagnetic storm was doing exactly what storms do. But storms don't collapse magnetic fields. They stress them. They test them. And Earth's field has been tested for billions of years. It's still here. The real question isn't whether the shield is down. It's whether the sun has more surprises in store, because the coronal hole is still open. The CME was just one event. Active Region 4299 is still active, and Solar Cycle 25 isn't done with us yet. So what else is lurking beneath the surface? What other magnetic flux ropes are winding up, ready to snap? What other coronal holes are waiting to open? We don't know. We can't know. Solar physics is predictive only in the broadest sense. We can forecast trends, but not specifics. We can say, there will be more flares, but not, there will be a flare on this date at this time. The sun keeps secrets. And that's terrifying, but it's also why we keep watching. Let's get something straight about Earth's magnetic field, It's not a shield in the way most people imagine. It's not a dome. It's not a wall. It's a dynamic, invisible structure generated by the churning of molten iron deep beneath our feet, and it extends tens of thousands of kilometers into space, far beyond the orbit of the moon. The field is shaped like a teardrop. On the side facing the sun, it's compressed by the solar wind into a bow shock, a sharp boundary where the wind hits and diverts around us. On the night side, the field stretches out into a long tail called the magnetotail, streaming away from the sun like a comet's tail. Inside this structure are the Van Allen belts, two donut-shaped regions filled with charged particles trapped by the magnetic field. These particles spiral along the field lines, bouncing between the northern and southern magnetic poles. This is our defense. Not a barrier, but a deflection system. When solar wind hits the magnetosphere, most of it flows around us. Some particles sneak in near the poles, following the field lines down into the upper atmosphere, where they collide with oxygen and nitrogen molecules and create auroras. The system isn't perfect, but it's effective. It's been protecting us for over 3 billion years, but it's not uniform, and it's not static. Earth's magnetic field varies in strength depending on where you measure it. Near the magnetic poles, it's stronger. Near the equator, it's weaker. And in one specific region, it's much weaker. The South Atlantic anomaly. If you've never heard of it, you should have. It's one of the most significant features of Earth's magnetic environment, and it's been expanding for decades. The anomaly is a vast area stretching from southern Brazil across the Atlantic Ocean to southern Africa, where the inner Van Allen belt dips closer to Earth's surface. In this region, the magnetic field strength is about 60% of the global average. Satellites passing through the anomaly are exposed to higher doses of radiation. Electronics can glitch. Instruments can malfunction. The Hubble Space Telescope shuts down its sensitive instruments when passing through the anomaly to avoid damage. The International Space Station schedules extra shielding for astronauts during transits. Why does the anomaly exist? It's a consequence of Earth's magnetic poles not lining up with the geographic poles. The magnetic North Pole is currently drifting across the Arctic Ocean toward Siberia at a rate of about 50 kilometers per year. The magnetic South Pole is drifting off the coast of Antarctica. This asymmetry creates regions where the field is stronger on one side of the planet and weaker on the other. The South Atlantic anomaly is the weaker side. Is it getting worse? Yes. Is it a sign of imminent collapse? No. The anomaly has been tracked since the 1830s, when German mathematician Carl Friedrich Gauss first mapped Earth's magnetic field using data from observatories around the world. Since then, the anomaly has slowly moved westward and grown in size. Scientists monitor it closely, not because it's dangerous to life on Earth, but because it affects satellites and space missions. Understanding how it evolves helps engineers design better radiation shielding and plan orbital paths that minimize exposure. But here's where the narrative gets hijacked. Some communities online have taken the existence of the South Atlantic anomaly and extrapolated it into localized field failures. They claim that similar weak spots are appearing in other parts of the world, specifically over seismically active regions like the San Andreas Fault in California. They point to magnetometer data showing fluctuations and unusual patterns, and they conclude that the magnetic field is collapsing in discrete zones. This isn't how planetary magnetism works. Magnetic field weakening is a global phenomenon driven by changes in the core's dynamics. It happens over centuries or millennia, not days or weeks. Localized fluctuations in magnetometer readings are almost always caused by external factors: solar wind interactions, ionospheric currents, or even human-made electromagnetic noise from power lines and industrial equipment. Seismic zones do exhibit electromagnetic effects. Tectonic stress can generate electric currents in the crust as rock fractures and releases piezoelectric charges. Water flowing through fractured rock can create streaming potentials. These effects are real, measurable, and well documented. They're used in earthquake research, not as predictors, but as indicators of stress accumulation. But they're not evidence of shield failure. They're evidence of a planet that's geologically active, where rock is under constant stress, where faults slip and release energy in earthquakes. California sits on the boundary between the Pacific Plate and the North American Plate, a zone of intense tectonic activity. Magnetometers there should show fluctuations. That's normal. So, where does the resonance structure claim come from? It's a misinterpretation of spectral analysis. When you analyze magnetometer data over time, you can decompose it into different frequency components, creating a spectrum. Certain frequencies might show elevated power, indicating periodic oscillations. If you don't understand what you're looking at, those oscillations can seem mysterious, even alarming. In reality, they're often caused by external sources. Solar wind fluctuations have characteristic frequencies. Ionospheric currents oscillate at predictable rates. Even Earth's own magnetic field has natural pulsations called geomagnetic pulsations, classified into different types based on their frequency and duration. These are well-studied phenomena, not anomalies, but if you frame them as spectral resonance structures indicating shield weakness, suddenly they sound ominous. Suddenly they fit the narrative. Language matters. Framing matters. A crack in a fingerprint isn't a crack in your hand. It's a pattern, a texture, a feature of complexity. Magnetic field anomalies are like that. They're patterns. They don't mean the system is broken. They mean the system is complicated. And here's the uncomfortable truth. We don't understand everything. Earth's magnetic field is generated by a dynamo process we can model, but not fully predict. The core is inaccessible. We can't send probes down there. We can't watch the currents flow. We infer everything from indirect measurements, from how the field behaves at the surface and in space. So when someone says, "What if there's something we're not detecting?" they're not entirely wrong. There could be subtleties we're missing. But jumping from "we don't know everything" to "the shield is failing" is a leap across a canyon, and there's no bridge. What we do know is that Earth's magnetic field has survived worse. It's survived superflares from the young sun billions of years ago. It's survived impacts from asteroids that vaporized chunks of the crust. It's survived reversals that lasted thousands of years. It's still here. We're still here. But the fear is understandable. The magnetic field is invisible. We can't see it. We can't feel it. We take it for granted until someone tells us it might be failing. And then, suddenly, it's all we can think about. So let's be clear. The shield is not down. The shield is stressed, dynamic, and constantly adapting. But it's holding. And it will keep holding. Unless the sun throws something at us that we've never seen before. Which brings us back to the question, what else is out there? We need to talk about the electric universe. Because if you've wandered into certain corners of the internet looking for answers about solar activity and Threeey Atlas, you've probably encountered this framework. And it's important to understand what it is and why it's appealing, even if it's not accepted by mainstream science. The electric universe theory, also called plasma cosmology in some circles, is a collection of ideas proposing that electromagnetic forces, rather than gravity alone, play a dominant role in shaping cosmic structures. Proponents argue that the universe is threaded with electric currents, that galaxies are connected by vast filaments of plasma, and that stars, including the sun, are not fusion-powered furnaces, but electrical phenomena powered by energy flowing in from these currents. It's a radical rethinking of astrophysics, one that challenges the standard models taught in every university. And because of that, it's been marginalized, dismissed, and labeled pseudoscience by the scientific community. But dismissal doesn't kill ideas. It pushes them underground, where they thrive in communities that distrust institutions and crave alternative explanations. The electric universe offers a narrative that's visually compelling, mechanistically intuitive, and deeply contrarian. It says, everything you've been told is wrong. For people who feel alienated by mainstream science, who see it as dogmatic or closed-minded, the electric universe is a revelation. It reframes solar flares not as magnetic reconnection events, but as electrical discharges. It reframes comets not as dirty snowballs, but as charged bodies interacting with the solar electric field. It reframes Earth's magnetic field not as a product of the dynamo effect, but as part of a larger circuit connecting the planet to the sun and beyond. Is any of this supported by evidence? Not in the way mainstream science defines evidence. The electric universe lacks predictive power. It doesn't produce models that match observations better than existing models. It doesn't publish in peer-reviewed journals. It doesn't integrate with the vast body of work in plasma physics, which is itself a legitimate and well-established field. But it offers something else, a sense of hidden knowledge. The idea that there's a deeper layer of reality that the experts are either ignoring or suppressing. And in the context of Threeey Atlas and the recent solar activity, the electric universe framework provides a ready-made explanation. Threeey Atlas, in this view, isn't just a comet. It's an electrically charged object traveling through the sun's electric field, disrupting the balance, triggering discharges that manifest as flares and CMEs. Its approach isn't coincidental, it's causal. There's no evidence for this. None. But the narrative is satisfying in a way that randomness isn't. It's easier to believe that the universe is interconnected, that events are linked by invisible forces, than to accept that we're watching unrelated phenomena unfold simultaneously by pure chance. And then there's the techno-signature angle, the idea that Threeey Atlas might not be a natural object at all. This comes from a different corner of speculation, one rooted in astrobiology and the search for extraterrestrial intelligence. When Oumuamua, the first confirmed interstellar object, passed through the solar system in 2017, some scientists, notably Avi Loeb at Harvard, suggested it could be an artificial probe sent by an alien civilization. The suggestion was based on Oumuamua's unusual shape, its tumbling motion, and its slight acceleration as it left the solar system, an acceleration that couldn't be fully explained by outgassing like a normal comet. Most scientists disagreed with the probe hypothesis. They offered alternative explanations. Oumuamua could be a fragment of a shattered planet, a chunk of hydrogen ice, or an object with an unusual surface composition that produced asymmetric outgassing. The debate continues. Threeey Atlas has not shown signs of being artificial. It has a coma, a fuzzy cloud of gas and dust surrounding its nucleus, consistent with a comet sublimating as it approaches the sun. Spectroscopic observations have detected carbon dioxide and water, molecules expected from icy bodies. Radio observations have detected emissions consistent with natural processes. But some still wonder, because Threeey Atlas exhibits a peculiar jet structure, a high-latitude jet that wobbles as the nucleus rotates. This is unusual, but not unheard of. Comets often have complex jet patterns driven by irregular shapes and uneven heating. Still, the wobble has fueled speculation. What if the jet isn't natural? What if it's a course correction, a thruster, evidence of control? Again, there's no evidence. But the question lingers, because we've only observed 3 interstellar objects. We have no baseline for what's normal. Oumuamua was anomalous. Comet Borisov seemed mundane. Threeey Atlas is somewhere in between. And in that uncertainty, speculation thrives. Online communities have analyzed every image of Threeey Atlas, zooming in on pixelated artifacts, claiming to see structures, patterns, signs of artificiality. Most of these are pareidolia, the human tendency to see faces and shapes in random noise. Some are deliberate hoaxes, manipulated images designed to generate clicks and engagement, but not all speculation is baseless. The scientific community is genuinely interested in interstellar objects as potential carriers of information about other star systems. If an object showed clear signs of being artificial, it would be the most significant discovery in human history. So, scientists look, they analyze, they publish their findings in journals where peers can scrutinize the data. None of those findings support the artificial hypothesis for Threeey Atlas. But the absence of evidence isn't evidence of absence, at least not conclusively, and so the speculation continues. What ties all of this together, the electric universe, the technosignature hypothesis, the magnetic field failure claims, is a deep human need to believe that what's happening now is significant. We want the universe to pay attention to us. We want events to have meaning. We want to be living through something historic, something that will be remembered. And maybe we are. Not because of cosmic conspiracies or hidden forces, but because we're witnessing the sun at a particularly active phase, because we're watching an interstellar visitor pass by, because our technology has advanced to the point where we can observe these things in real time and share them instantly across the globe. The story is remarkable, even without the embellishments. But the embellishments are what make it spread. They're what make people care. So here we are, caught between two worlds. The world of data and peer-reviewed science, where events have explanations rooted in physics and chemistry and mathematics. And the world of narrative, where events feel connected, where the sun's opening and the comet's arrival and the alignment of planets are chapters in a larger story we're only beginning to understand. Which world is real? Both, in different ways. And the tension between them is what makes this moment so compelling. Because even as we debunk the conspiracies, even as we push back against the pseudoscience, we can't quite shake the feeling that something big is happening. And maybe it is. Just not the way anyone expected. Let's step back from the speculation and talk about what we actually know, what we've actually observed, what the data is actually telling us about Threeey Atlas and the current state of the sun and space weather. Because even stripped of conspiracy and cosmic alignment theories, the science here is genuinely fascinating. Threeey Atlas is a carbon dioxide-rich comet. We know this from spectroscopic observations conducted by multiple observatories shortly after its discovery. When sunlight hits the comet's nucleus, it heats the ice, causing it to sublimate directly from solid to gas. That gas forms the coma, the fuzzy envelope surrounding the nucleus. By analyzing the wavelengths of light absorbed and emitted by the coma, scientists can determine its chemical composition. Carbon dioxide is prominent, so is water. These are common volatiles in comets native to our solar system, but the ratio between them can vary depending on where and when the comet formed. Threeey Atlas's composition suggests it formed in a cold, outer region of its home star system, similar to our Kuiper belt or Oort cloud, before being ejected into interstellar space. The James Webb Space Telescope has contributed observations, using its infrared instruments to penetrate the coma and study the nucleus itself. Early data suggests the nucleus is small, likely just a few kilometers across, and irregularly shaped. This is typical of comets. They're not spheres, they're rubble piles, loose aggregations of ice and rock held together by weak gravity. Radio observations have been equally valuable. Telescopes like ALMA in Chile and the Green Bank Telescope in West Virginia have detected molecular emissions from the coma, confirming the presence of organic compounds and icy grains. These observations help scientists understand how interstellar comets differ from or resemble their solar system counterparts. One particularly intriguing finding is the wobbling jet. Observations show a jet of gas and dust erupting from the comet's surface at a high latitude near one of the poles. As the nucleus rotates, the jet wobbles, sweeping across space like a lighthouse beam. This behavior is consistent with a rotating, irregularly shaped nucleus, where localized heating creates asymmetric outgassing. But it's unusual. Most comet jets are more stable, emanating from specific active regions heated by the sun. The wobble suggests the nucleus might be tumbling chaotically, or that the active region is at an angle to the rotation axis. Either way, it's a feature that planetary scientists are studying closely, because it offers clues about the comet's internal structure and thermal properties. None of this is evidence of artificial origin. All of it is consistent with a natural comet doing natural comet things. But it's complex and surprising, which is why it's exciting. Now, let's talk about the sun, because while Threeey Atlas is passing by, the sun has been anything but quiet. The trans-equatorial coronal hole is real. Satellite images from NASA's Solar Dynamics Observatory clearly show a vast dark region stretching across the sun's equator, a zone where the magnetic field is open and high-speed solar wind is streaming out. Coronal holes are a natural part of the solar cycle. They're more common during solar minimum, when the sun's magnetic field is simpler and more organized. But we're not at solar minimum. We're approaching solar maximum, expected around 2025 or 2026. The presence of a large coronal hole now suggests the sun's magnetic field is in a transitional state, more chaotic than models predicted. This doesn't mean anything is wrong. It means the sun is complicated. Models are approximations. They capture the general behavior, but miss the details. The sun doesn't follow a script. It improvises. The recent M8.1 flare from active region 4299 is another example. The sunspot group appeared suddenly, grew rapidly, and unleashed a powerful flare, followed by a full halo CME aimed at Earth. The geomagnetic storm that followed was forecasted accurately. The models worked. The infrastructure held. Auroras were spectacular. Radio blackouts were brief. Life went on. But the storm was a reminder of what's possible. If the flare had been X-class instead of M-class, if the CME had been faster, if the magnetic orientation had been just right, the effects could have been more severe. We were lucky, and we'll need to keep being lucky, because Solar Cycle 25 isn't done. Active regions will continue to flare. CMEs will continue to launch. Some will miss Earth entirely. Some will graze us. Some will hit directly. It's a numbers game, a cosmic lottery where we're buying tickets every time the sun rotates. The Parker Solar Probe, humanity's closest emissary to the sun, is currently diving through the corona, gathering data that will revolutionize our understanding of solar wind acceleration and magnetic field dynamics. The probe has already survived temperatures exceeding 1 million degrees, skimming just a few million kilometers above the sun's surface, closer than any human-made object has ever been. Data from Parker is revealing that the solar wind is more turbulent, more structured, and more energetic than models predicted. There are jets, switchbacks, magnetic islands, waves. The corona is alive with activity, and we're just beginning to map it. Meanwhile, the Vera C. Rubin Observatory in Chile is preparing to begin its Legacy Survey of Space and Time, a 10-year project that will image the entire visible sky every few nights, detecting asteroids, comets, supernovae, and transient phenomena with unprecedented speed and sensitivity. When fully operational, Rubin will discover thousands of new objects every night, including more interstellar visitors like Threeey Atlas. Because here's the thing, Threeey Atlas isn't rare, it's just the third one we've found. Models suggest hundreds or even thousands of interstellar objects pass through the inner solar system every year. We've only detected 3 because our telescopes weren't sensitive enough until recently. As detection technology improves, we'll find more. Maybe dozens per year, maybe hundreds. And each one will be a time capsule from another star system, carrying chemical signatures and structural clues about the conditions where it formed. Some will be icy comets. Some will be rocky asteroids. Some might be fragments of shattered planets, or even, someday, artifacts from another civilization. We're entering an era where interstellar objects are no longer curiosities, but data points, part of a growing catalog that will teach us about the diversity of planetary systems across the galaxy. That's the real story here. Not cosmic conspiracies or shield failures, but the slow, steady expansion of human knowledge. We're learning to read the sun. We're learning to interpret the chemistry of alien comets. We're learning to track space weather and protect our infrastructure. It's not dramatic in the way a disaster would be dramatic. It's not a narrative with a clear beginning, middle, and end. It's incremental, cumulative, and sometimes frustratingly slow. But it's real, and it's happening right now. As you read these words, the sun will continue to flare. Threeey Atlas will continue its journey, fading into the darkness beyond Neptune's orbit, never to return. The magnetic field will continue to shield us, fluctuating and adapting as it has for billions of years. The planets will continue their orbits, occasionally aligning in ways that look significant but aren't, and will continue to watch, to measure, to speculate, and to wonder. Because that's what humans do. We look up, we ask questions, we imagine possibilities, and sometimes in the space between what we know and what we fear, we find something worth discovering. The universe doesn't need to be conspiring against us to be awe-inspiring. It just needs to be itself. Vast, complex, and full of surprises we're only beginning to understand.